All right, this is going to be a walkthrough on a Pwn challenge from the University CTF 2025 Tinsel Trouble. This is the medium challenge that was given, or the hardest challenge that was given for Pwn during this event. Our team ended up full clearing, just shy of fifth place, so we ended up in sixth. But let's dive into this, and I'll explain how I solved this challenge and the primitives that are used to uh, beat it. So hopping right into the decompilation in Ghidra, it's a non-stripped binary, so we can just open it and read it. First thing to notice here is that we are supplying input for the tinkerer name in the console state, and shortly after it is directly reflected with printf with no arguments, meaning that we can just supply an arbitrary input and get printf leaks or writes or whatever we really desire. Let's see. The other things that are important for solving the challenge, uh, when you read through here, a file structure is created and stored in core log. We give it a name. This other stuff's not really relevant for the solve. Feeding a fragment. Thing to see here is that we can allocate a chunk of our chosen size. The only thing is we can only choose a size below 501. And then we can write to that chunk. Next option here is the cancel routine. This just closes the file structure. But also an important thing to see here is that it calls fclose on it, but it doesn't set it equal to null. And it checks right here if it's equal to null, meaning there's no active one. But when we close it, it should also reset it to null to show that there's no longer an active one, but it fails to do that. And then commit routine is just writing to the core log. So let's see how we can abuse these to solve the challenge. Okay, so looking right here to solve the first part of solving the challenge, I will display here we are leaking a stack address as well as a pi address, so we can gain some information on our binary here. So I'll show right here. This is an address on the stack, and then this is a address of the binary, and you'll see here that it's offset 0, so if you subtract 40 or hex 40 from it, we are at the base of the binary. Oops. Yep, so that's what we're doing here. We're rebasing the binary, so later on when we index a function in the binary, it knows exactly where it lives. And also, let me show that function really quick. That is the win function. It's called gingergate. If you call it, it calls system. So yes, and this stack address here, I chose to target the, I think it was commit routine. Okay, yeah, the commit routine function. I targeted the return address. So if we break there, let's start one. Give it something to commit. I'll commit. We'll look at the stack address here. And now our address from earlier. So if we take this and I believe subtract this. Okay, wait. We find the difference between these two values and it's 2118. So you see we take our leak, add 2118, and we get this address here. So now we have information that we need. We know where the win function lives, and we know where the stack pointer lives. So we can really get into the exploitation part. So the main thing here is that we're exploiting a file structure And I'll show you even how we even get to the file structure. So just running the program, I'll give it just random input. I will open the file. This is creating the file structure right here. So, and immediately I'm going to close it. Oh, sorry, I clicked the wrong value. Okay, name 3 this time instead of 4. Cancel routine calls fclose. So you can see here, routine has been canceled. And now if we look at the tcache bin, the structure lives here. So let's look in Python just to see that value in decimal. That is less than 501, which means we can reallocate this when we are doing the feed fragment function. So we can supply the number here to reuse this chunk out of tcache, essentially meaning when we reallocate it, we will control where the program thinks a file structure lives. So I'll go ahead and display that again right here. We'll call 2. We'll use 470. Just give it some random input here. Now we'll look at the bins. See that address is gone because it's not being used. And then we'll break at fputs. Call 4. Okay, we'll see here, fputs. The chunk that we just allocated, the stream, is the same as what it believes is the file structure. So at this point, we completely control the file structure. And we can write up to 465 bytes or 475 bytes of what's at the file structure. And what's nice about PwnTools is that it has a built-in file structure class that we can use to craft a malicious file structure. And I'll show you right here the flow of the exploit. So again, as I showed, we open a file and we immediately close it. This puts that chunk into tcache for us. We reallocate it using the feed fragment function. And then what we want to write at the chunk, or where the program believes a file structure lives, we will create a false file structure that'll allow us to get an arbitrary write. And the way that this works is that because file structures are based around buffers, meaning instead of constantly opening and closing a file, it uses a buffer to like feed input into, and then once that buffer is full or the file structure is being closed, then it opens the file and throws in a chunk of what was supposed to be written, as opposed to like constantly opening and rewriting for every single write. So we trick the file structure, or we trick the program into thinking that the file structure is writing here. So we trick it to thinking that the buffer for the content is at the stack leak that we have. So we're saying the base of it is here at the leak minus hex 20. And we say currently in this buffer, we are at the stack leak. And then the end of the buffer is stack leak plus hex 20. The hex 20, it doesn't really matter too much. We just want to make sure that it's farther than the payload. So like if our payload down here that we're going to input was greater than hex 20, it would cause it to flush the buffer before like the complete payload is inserted. Um, but yeah, so the condition that you need here is that the base needs to be less than the pointer, which needs to be less than the end. So it's just a standard setup. That's very logical thinking. But here you go, we're sending that fake file structure here, and it is overwriting what the program thinks is the file structure. So now when we go to craft our payload, what we're doing is we're calling this function in feed fragment, which allocates whatever, and then we write to that chunk. So now in memory, that is our like quote unquote stream. that it's living on the heap. So when we call commit routine, it will take that fragment and it'll write it to our buffer inside the file structure, essentially writing whatever's right here into our stack leak. And I will show you here this working. Oops. Okay, we can see now we are at our stack leak. This is the address, which we calculated here. Pi leak shows the base of pi right here. And when we're returning from this function now, we are going to exactly where we wanted to, gingergate plus 5. And I'll show you why we did gingergate plus 5. I will do it normally without gingergate plus 5. And we'll see what happens. So we step here, and we get our move apps. The stack is not 16 bytes aligned, so we can't exactly write. Well, I guess we could write a ret gadget, but I don't know. A simple trick that I like to do is I will jump over like this instruction here because this changes or misaligns the stack by 8 bytes. So if we just remove this push, we realign the stack. So I'll change that back. Oops. And then rerun the solve script. And we now have a shell. So yeah, that is how you can abuse file structures to solve this CTF challenge. File structures are a very strong primitive, and usually if you are able to overwrite them, you can almost always get RCE. So yeah.